We're in chapter 7, section 7-1, which has to do with the Laplace transforms. Now, in the last chapter, chapter 8, you're going to see that in your next partial differential equation class, or your intro to quantum mechanics class will be the next time you see chapter 8. Chapter 7, however, has to do with Laplace transforms, and all the engineers are going to be required to use Laplace transforms to solve differential equations. So that's just one of those things. Okay, so Laplace transforms. And just remember that there was a time when there wasn't radio and TV, and mathematicians had a lot of time to spend, so they could come up with all this cute stuff. And so that's just the way it is, and we're stuck with it. So anyway, I am the king of a kingdom, and I decided that multiplication and division are never going to be used again in my kingdom. And so we have this domain that in which multiplication and division are used, and I am banning it. We can't use it at all. So what are we going to do? Well, we're going to use addition and subtraction only. We're not going to use multiplication and division because I'm the king and I can tell you that that's the way it's going to be. So the mathematicians get together and they say, okay, no problem. What we're going to do, whenever we have a multiplication problem, we're going to transform it over to the domain of log. And so we're going to do a log, and then we're going to add and subtract those logs, and that's going to be the same thing as multiplying and dividing. And when we want the answer back and we want to tell the king the right answer, we're going to do an anti-log. And when I do that, then I'll know what to. So if I have 2 times 2 over here, I'll change that to log 2 plus log 2. And then I'm going to do an anti-log and go back the other way until the king the right answer is 4. And I'll never do multiplication or division again. Okay, so that's the theory of the situation. So now we come to a situation where in chapters 1, part of 2, 3, and 8, we're solving things in the time domain. So we have f of t, and we're using calculus and all kinds of other higher math functions to do it, and we say, well, that's a little boring. I want to solve differential equations by just using algebra. I don't want to have to go and do that integral 0 to infinity stuff anymore. I don't want to have to do any of that. I want to use algebra. And I'm going to solve my differential equations. So that's what I'm going to do. So, okay, that seems like a reasonable thing to do. So what I'm going to do is I'm going to use something called a Laplace transform, and I'm going to make f of t become f of s. And then I'm going to use algebra on the differential equation, and then when I get it in a form that I like, I'm going to come and take that form and use a reverse Laplace transform and get back to the time domain to get the right answer. Okay, so that's what I'm going to do. I'm going to, just like I did before, I didn't want to do multiplication and division. I'm not going to do it. I'm going to go to the S domain. So I'm leaving the time domain. I'm entering the S domain, and I'm using algebra, and then I'm solving for f of t that way. Okay, that seems like a reasonable thing to do. So how are we going to do that? Well, the Laplace transform of f of t. And we're going to call that capital F of s, or the Laplace transform of, if we could have x of t, for example, we'd call that capital X of s. We could do that either way. And so we have a definition, and it says the Laplace transform of f of t is going to be the integral 0 to infinity of f of t e to the minus st dt. Okay, that seems like a reasonable thing to do. And as long as this integral converges for some value of s, then everything's fine, and we're all set, and we can do that. Okay, well, we can't take an integral 0 to infinity, we know that, but we can do limit as b goes to infinity of integral 0 to b of f of t e to the minus st. So we take the improper interval, turn it into something that we can deal with, and solve it that way. Okay, so that's our plan. When we look at figure 7.1-1, and I don't have written down what page that's on, so you have to go looking for it. We have a bunch of Laplace transforms already. So we have f of t's turning into f of s's that we can use. And we find that if we have f of t plus g of t, then the Laplace transform is going to be f of s plus g of s. Capital letters there is what we use. Okay, if we have a f of t, where a is some number, some real number, then that's just going to be a f of s. So that basically means that the Laplace transform is linear. If I do a 1, I'm going to have 1 over s. If I have a t, I'm going to have 1 over s squared. If I have t to the n, so t to the n, the Laplace transform is going to be n factorial divided by s n plus 1. Okay, that's probably okay. E to the at, and we'll do most of these to show you that they're right later. E to the at, 1 over s minus a, sine at, a over s squared plus a squared. Cosine at is going to be s over s squared plus a squared. And several more in that table. So we have hyperbolic sine t a t. Hyperbolic sine a over s squared minus a squared. Hyperbolic cosine s over s squared minus a squared. And then we always have to throw some weird thing in. So if I have t raised to the a, where up above we had t raised to the n, where n is some integer, that's fine. Well, n doesn't have to, then t to the a doesn't have to be an integer, it's just any value at all. And we end up, that's going to be gamma function a plus 1 divided by s to the a plus 1. Isn't that nice? Oh yeah, gamma functions. Oh, aren't they cool? How are we going to deal with gamma functions anyway? Show of hands, how many have seen gamma functions before? By the way, on the website there's a better Laplace transform table that I use for solving problems. And when I solve a problem and I use a number, it's off that Laplace transform table. So you should print that out so that you have it. It's in section 7-1. So section 7-1 has a better Laplace transform table than is in your book. Anyway, the gamma function of x is going to be integral 0 to infinity, e to the minus t, t to the x minus 1, dt. And that particular integral we're never going to solve because we're going to do something. Anyway, the gamma function's at improper integral again. We're never going to solve it. We're going to do something different. In my Handbook of Chemistry and Physics on page A191 is a table of gamma function going from 1 to 2. And that's all you would need if you wanted to do something weird. But in this class, we'll say the gamma function of 1 gets to be 1. And the gamma function of 2 gets to be 1. Oh, isn't that lovely? That's just great. And the gamma function x plus 1 becomes x gamma function x. So if I have integers, then the gamma function, that's not a gamma, the gamma function of n plus 1 is just going to be n factorial. So the gamma function is something that's giving us a factorial notation for numbers that aren't integers, is basically what it's doing. Okay, and then of course we have to get weird. We're always weird. So the gamma function of a half is going to be the square root of pi over 2. Okay, well that seems reasonable. So just following the simple rules that are there, that should solve all the problems that we have to do. Okay, so back to the issue. Is our Laplace transform table correct? So the first guy we're going to look at is f of t is equal to 1. And we say, well, what is f of s? Well, f of s is going to be integral 0 to infinity 1 times e to the minus st dt. And so we're going to change that limit. B goes to infinity, integral 0 to b, e to the minus st dt. And we end up with limit b goes to infinity, e to the minus st divided by minus s, evaluated at 0 and b. Okay, that seems reasonable. Limit b goes to infinity. So I would have e to the minus sb over minus s minus e to the 0, which is 1, over minus s. And we look at limit b goes to infinity. Well, that makes this guy go to 0, so that's fine. So our answer is going to be 1 over s. And in our Laplace transform table, we said that the Laplace transform of an integer is 1 over s. So that's pretty good. What's the Laplace transform of 2? Well, that'd be 2 over s. So that's the way that is. All right, one down, several more to go. F of t is equal to t. So we have f of s is going to be integral 0 to infinity t e to the minus st dt. Again, we say, well, I don't want to deal with the improper integral, so limit b goes to infinity, integral 0 to b, t e to the minus st dt. And then we say, well, you know, I sort of remember a integration by parts. And how does that go? That goes duv dvu is equal to v prime u plus uv, or whatever it is. And then I integrate both sides, and I bring one of them to the, I keep one over here. So integral uv, integral v prime u is going to equal vu minus integral v u prime. So I remember that, and I say, well, okay, well, what do I have here? Well, if u is t, then u prime is 1. And if v prime is e to the minus st, then v is going to be minus e to the minus st divided by s. Okay, so now we come back to our limit. B goes to infinity. And what do I got? I got t, I want v minus e to the minus st over s times u, which is t, evaluated at 0 and b, minus integral 0 to b of v minus e to the minus st over s times u prime, which is 1 dt. Okay, well, that seems fair, I guess. I put the b in, and I go to infinity. I put the 0 in, and I get a 0. So that term drops out. This term goes away. It's going to be 0. And I end up with limit b goes to infinity minus, and minus e to the minus st over s squared. That becomes a plus sign, evaluated at 0 and b. Okay, limit b goes to infinity, and I've got minus e to the minus sb over s squared minus 1 over s squared. And as I go to infinity, this guy goes to 0, and I get 1 over s squared, which is, again, what I was hoping I would get before I started the process. All right, one more. Well, so maybe 2 more, who knows. F of t is equal to e to the at. So f of s is equal to 0 to infinity, e to the at, e to the minus st dt. So I've got limit b goes to infinity, integral 0 to b, e to the a minus s t dt. And I've got limit b goes to infinity, and I've got e to the a minus s t divided by a minus s, evaluated at 0 and b. Okay, so I put the b in, and I get limit b goes to infinity, e to the a minus s b divided by a minus s minus 1 over e to the 0 is 1 over a minus s. Okay, as I go to infinity on b, that guy goes to 0, and I got a minus sign there. So I've got final answer. The Laplace transform of e to the at is going to equal 1 over s minus a. And if I had the Laplace transform of e to the minus at, then I'm going to have 1 over s plus a. Am I not? Yes, I am. Okay, so now I promise you weirdness, so now it's time for weirdness. We're going to look at, for a moment, f of t is equal to e to the j omega t. You like j, or would you rather have I? E to the I omega t. Which one do you want to use? So either one, j or I, are both going to equal the square root of minus 1. They're both imaginary numbers. And I don't think the author does this, so it really doesn't matter. We'll use the I guy. Okay, so I want the Laplace transform of e to the I omega t. Okay, well, that seems like a reasonable thing to do. Integral 0 to infinity, e to the I omega t, e to the minus st dt. Limit b goes to infinity, integral 0 to b, e to the I omega minus s t dt. Okay, so limit b goes to infinity, integral, no integral, because we're going to solve it right here. Okay, e to the I omega minus s t divided by I omega minus s evaluated at 0 in b. Okay. Limit b goes to infinity, e to the I omega minus s b divided by I omega minus s minus, this becomes 1 divided by omega, I omega minus s. Okay, well, that seems like a reasonable thing to do. As I go to infinity, I'm going to let my s be bigger than I omega, so obviously this is going to go to 0. And my answer is going to be 1 over s plus minus I omega, because I have a minus sign there, so I'm going to turn it around on the bottom. And my 9th grade algebra teacher always told me to rationalize the denominator, s plus I omega over s plus I omega. Okay, so that looks okay. And then I'm going to have s plus I omega divided by s squared plus omega squared. And then I'm going to say, oh gee, what is e to the I omega? Well, Euler told us that was cosine omega plus I sine omega, right? He told us that. Okay, so if I take the Laplace transform of that, I should get the Laplace transform of this. I should do that. And then I say, well, I have that Laplace transform already, and what it is s over s squared plus omega squared plus I over omega over s squared plus omega squared. So obviously, that being the case, the Laplace transform of cosine omega is going to be s s squared plus omega squared. And the Laplace transform of sine omega is going to be omega over s squared plus omega squared, which is exactly what our Laplace transform table tells us it is. Okay, so looks like I'm going to do 2 more, and then I'm going to start working problems probably in the next video, because we don't want this one to go too long. So we're going to look at the hyperbolic sine and the hyperbolic cosine. That's what we're going to look at. All right, so the Laplace transform of the hyperbolic sine is going to be limit b goes to infinity, integral 0 to b, and e, and we need an a there, so we're going to put an a here and an a there and an a out there to make it nice. So e to the at minus e to the minus at over 2 e to the minus st dt. Okay, well, that seems like a reasonable thing to do. Limit b goes to infinity, 1/2 integral 0 to b e to the a minus st minus e to the minus a minus st a minus st e to the dt. Okay, so we got limit b goes to infinity, 1 over 2 e to the a minus st divided by a minus s minus e to the minus a plus st divided by minus a plus s. Okay, that seems all right. I got a minus sign here and a minus sign there. I'm going to make it plus altogether, plus plus. And I need to evaluate this between 0 and b. Okay. Limit b goes to infinity, 1/2 e to the a plus s t, that's a b, divided by a minus s minus, I put a 0 in there, I get 1 over a minus s, and then I get a plus sign, e to the minus a plus s b over a plus s, and then I get a minus 1 over a plus s. And I put brackets that you can't see around those things because I ran out of room. That guy goes to 0, this guy goes to 0. I have limit b goes to infinity. Well, I don't even have to do that anymore, do I? I get 1/2 1 over s minus a plus 1 over well, it'd be a minus s plus a. Okay, well, that seems like a reasonable thing to happen. I combine like things, so I get 1/2, and I have s plus a minus s minus a divided by s squared plus minus a squared. S squared minus a squared. So I have the s's go away. I have two a's, and so the 2 goes into the 2a, and I have a over s squared minus a squared. And with that, I'm done. That's the Laplace transform. So the Laplace transform of hyperbolic sine of AT is going to be a over s squared minus a squared. Now, I can do the same thing over again, and but I'm not going to. I'm going to say that, just tell you that the Laplace transform of the hyperbolic cosine of AT, and I could go through everything that I did, is going to be s over s squared minus a squared, but I'm not going to do that. Okay, that's half of the first section. I'm going to stop there and then start another video.